Greetings, my calculus students. Today we're going to be going over L'Hopital's rule and some optimization problems. So we're going to start off with section 4.4 and then we're going to round off with a few examples from section 4.7. And the optimization problems kind of just another way of saying word problems, and so we'll just do a couple examples from that so you get the idea of how it goes. So first off, let's focus on L'Hopital's rule. L'Hopital tells us how to deal with indeterminate forms. And so an indeterminate form, it shows up when we have 0 divided by 0. How can I fit nothing into nothing? One of the ways I tell people to visualize this is I'll tell people to try and imagine having no clothes and trying to fit them into a suitcase of 0 volume. How many clothes can you fit? It doesn't make sense, and so neither does 0 divided by 0. Also, something that is an indeterminate form is infinity divided by infinity. If I have an infinite amount of clothes and a suitcase of an infinite size, how many of those clothes can I fit into the suitcase? It's a question that doesn't make sense. Neither does infinity divided by infinity. All right, so this brings us to L'Hopital's rule. If we have the limit as x approaches a, we've got two functions here, f of x divided by g of x. If we get infinity over infinity, it could be positive or negative, doesn't matter. Or if we get 0 divided by 0, maybe go ahead and include positive or negative in our forms there. That's a comma. Then, recall that, these two are the same. Then the limit as x approaches a of f of x over g of x, note we have the same limit, is f of prime of x over g prime x, right? And so this is the only time that you can have this guy turn into this guy, because if you recall, when we take the derivative of a function divided by another function, we use the quotient rule. But right now we're using L'Hopital's rule because we're dealing with a limit. The only time you get to do this is if you're dealing with a limit. All right, so note that I've got the two-sided limit a. This also works for the one-sided limit from either direction. It also works if x is approaching infinity, positive, or infinity, negative. So let's do some examples. So first thing you do is you plug in 0 to see what happens. Cosine of 0 is 1. 1 minus 1 is 0. And in the bottom we got simply x. So you're going to get a 0 over 0, which is an indeterminate form. And so we're just going to take the derivative of the top and the derivative of the bottom. So the derivative of cosine of x is negative sine x. Derivative of 1 is just 0. And then we've got derivative of x is 1. Now we apply the limit. And so this becomes negative 0 over 1, which is just 0. And there it is. That's our answer. Okay. All right, so for this guy, if you plug in 4, you will notice that the top will become 0, and so will the bottom. We'll have a 0 over 0 error. So we can apply L'Hopital's rule. Limit as x approaches 4. Take the derivative of the top. 2x minus 2 over 1. All right. Put in the 4. And we'll get 8 minus 2, which is 6. And so now we move on to the next one. If you plug in infinity here, you will get e raised to the infinity divided by infinity, which of course is the same as infinity over infinity. That is an indeterminate form, so we can apply L'Hopital's rule. So the limit as x approaches infinity, derivative of e to the x is simply e to the x. Divide that by 1. And so we plug in our infinity, e to the infinity, which is just infinity, right? E raised to the infinity is just an even bigger infinity. And so kind of think about this for a second, you know. We've got an infinity down here, and we've got an infinity up here. The fact that the result is infinity tells us that this infinity right here on the top is infinitely larger than this infinity right there. Okay, so let's go ahead and take a look at these on the graphs. We make sure we get a good picture in our heads of what's going on. Right, so we've got the first example graphed here, that is cosine of x minus 1 all over x. And so if you look here at 0, which is the limit we're looking for, it is in fact undefined. You know, it's definitely approaching 0, as you can see, but it is undefined. If we plug in, you know, f of 0 here, it shows up as undefined. Okay, good. So let's take a look at the second example we worked on. We have g with x squared minus 2x minus 8 on the top and x minus 4 on the bottom. And we were looking for the limit as x goes to 4. And so, you know, if you plug in g of 4, you will get something that is undefined, which is what we expected because it's a 0 over 0. And when we look at that point, you know, indeed it is undefined, but note it is approaching something. It is approaching 6 right there. All right, so last one, the third example that we looked at. You know, so you can kind of see as we get in close, 1 over, you know, this does look like the graph of 1 over x when we're near 0, but when we get away from that, e to the x takes over, and as you can see, e to the x, you know, is approaching infinity. This whole thing is approaching infinity as a result. So that's kind of a good overall picture of everything. You zoom out, and so you can see here, you know, it is actually accelerating rather quickly. Before we even get to 10, we've already surpassed 100. All right, so let's go on to the back, or the next part. Sorry, not the back yet. Indeterminate difference. So it might be logical to think that, oh, we've got infinity minus infinity. Well, the result must be 0, right? Because we're subtracting infinity from infinity. But what's one of the things we've been saying? Well, we've been saying that some infinities are larger than others, just like with e to the x over x, right? Both these numbers approach infinity, but e to the x gets bigger much, much faster. When we take the limit, this e as x goes to infinity, e to the x is actually a much larger infinity. And so we cannot say this equals 0. Right? You cannot say that. So make sure you never say this. Go ahead and take a moment, pause the video, and put your hand over your heart and say, I will never, ever, ever say that infinity minus infinity is 0. And you should make a similar pledge for 0 divided by 0. It's undefined. Never say 0 divided by 0 is 0. Never. All right, so this is in fact undefined. All right, so we're going to go over some different ways to deal with functions that are of this order. And so if you notice here, you plug in infinity, and you're going to get infinity minus infinity. Now, we've already discussed that this guy is going to approach infinity much larger than this guy. So we already know that, well, it's not going to be 0. There's no way it can be 0. As a matter of fact, based on what we've seen, it's going to be positive infinity, but we can't just go off of what we know of these examples. We have to work through it to show that this is the case. So in this one, you might think this is being a little creative, but it just takes an eye to start seeing these things. We're going to factor out an x. And when we factor out an x, we get e to the x divided by x minus 1. And so you'll note that if you distribute this x here to both of these terms, the first term, the x's cancel, so you get e to the x back. In the second term, we've got a negative 1 times x, and that answer that is minus x. So we will get everything back if you distribute everything through. All right, so let's go ahead and take these limits. You might recall that since this is a product of two functions, we can simply break it up with multiplication rules. Like so. First guy, right here, that's clearly going to be a positive infinity. And multiplied by this guy, well, we know e to the x over x. We've already done this one. Remember, that was the last example we did right here. E to the x over x equals infinity. When you're taking the limit as x goes to infinity, of course. So you get infinity minus 1. Now, 1 less than infinity is still infinity, so this becomes infinity times infinity, which is just an even larger infinity. And so that went right with our intuition back here. All right, so that's one way of dealing with an indeterminate difference when you're taking the limit. Let's look at another one. Here, notice, if you plug in infinity minus infinity, because infinity cubed, infinity squared, it's going to be the same. And so this is indeterminate. We can kind of see that this one's probably going to be the larger infinity, so we suspect that the answer will be positive infinity, but we have to work it out. So what we do is we're going to factor out an x again. Only this time not just an x, we can factor out a whole x squared. And so we get x minus 1. And so now we simply apply the limit to both functions, right? This one and this one. And we're going to end up with, the first term is infinity squared. The next guy is infinity minus 1, just infinity. And so we end up with infinity, because infinity times infinity is infinity, which matched our intuition there. All right, awesome, good. Let's move forward on to the back this time. And we're going to talk more about some indeterminate forms. And let's say we've got something of this form right here. That is, we've got the limit as x goes to a of f of x, only f of x is raised, has an exponent of some other function, g of x. Then the following types are independent. And we'll note we've got 3 types that are indeterminate when we're dealing with a power. If we have this right here, we could have a 0 over 0, right? If you take the limit, you get 0 over 0. 0 to the 0th power is indeterminate. We could get this form, infinity raised to the 0, right? You may recall that anything to the 0th power is 1. Any finite number to the 0th power is 1. Infinity is anything but finite. All right, and over here you may recall 0 is just 0, but anything to the 0th power is 1. So we've got an indeterminate action going on here. So those two, yes, they make a lot of sense. One that may not make a whole lot of sense to you might be 1 raised to the infinite power, because you think, well, let me think here. Well, 1 times 1 times 1 times 1 times an infinite number of 1s, isn't that just 1? Well, if that were only what we were doing, then yes, that would be true. But we could have another situation. We could have the limit as m goes to infinity of 1 plus 1 over m raised to the m. And so what you might note is that this, when you take the limit, it looks like you got 1 to the infinity. And if you said the answer was 1, you would be wrong, because we recognize this as the definition of the natural number e, also known as Euler's number. And so what's going on here, it's not just 1 to the infinity. What's going on here is that we get 1 plus some teeny tiny delta raised to the infinite power. And so that teeny tiny delta is what adds some of the extra digits. So that's why 1 raised to the infinite power is not 1. All right, so we've got some strategies to deal with these guys. And so it'll be this. First, we're going to set the function you are taking the limit of equal to y. That is, we're going to say y equals f of x raised to the g of x, right? No, we're not dealing with the limit right now. And now we take the natural log of both sides. So we've got the natural log of y equals g of x times the natural log of f of x. All right, so once you get it like that, you're going to be taking the limit and solving for it after that point. Let's look at this example, and I think it'll make a lot more sense after that. So the first thing we do is we set this guy equal to y. So y equals 1 plus sine of 4x raised to the cotangent of x. And I should probably verify to you that this is an indeterminate form. If you plug in 0 in right here, you're going to end up with sine of 0. Sine of 0 is 0. So you end up with a 1. And cotangent of 0, keep in mind cotangent, you have cosine over sine. And it's coming from 0 positive. And so we're going to have an infinite power there, right? We've got 1 raised to an infinite power. All right, so we're going to take the natural log of both sides. Natural log of y equals the cotangent of x times the natural log of 1 plus sine 4x. Nope, looks like I'm starting to run out of space. All right, so now that we got this, we're going to go ahead and take the limit of both sides. Oops, did not mean to do that. There we go. The limit of both sides as x approaches 0 from the right, the limit as x approaches 0 from the right. All right, so first off, let's go ahead and restate this guy. The limit as x approaches 0 from the right, and we'll have the natural log up top of 1 plus sine of 4x, and in the bottom we're going to have simply tangent of x, right? Because cotangent is the same as 1 over tangent. Alright, so if you plug in 0 for tangent, you're going to get 0 in the bottom. If you plug in 0 up in the top, you're going to get negative 0 in the bottom if you plug in the 0. And then here you have the natural log of 1 plus 0, which is the natural log of 1. Natural log of 1 is 0 over 0. Right? E raised to what power is 1? That's 0. Okay, so we can use L'Hopital's rule. And so we take the limit as x approaches 0 positive. And so in the bottom we take the derivative of tan, so that's going to be secant squared x. And up in the top, we simply, becomes a fraction, 1 plus sine of 4x in the bottom, and in the top we take the derivative of what's inside, so that's going to simply be 4 cosine of 4x. Alright, so let's do some more rearranging here. And so the limit as x approaches 0 positive. Recall that secant squared is simply 1 divided by cosine squared. So we can bring that up in the front. Cosine squared x. And then multiply by 4 cosine 4x divided by 1 plus sine of 4x. Alright, so let's go ahead and plug the 0 in, and we should be able to get a nice result here. Cosine of 0 is 1, and 1 squared is 1, multiplied by 4 cosine 4x. So we have 4 times cosine of 0, which is 1. And divide that by 1 plus sine of 0, which is 0. And so all that becomes 4. Good. So the next thing we're going to do, first we're going to restate what we have. The limit as x approaches 0 positive of the natural log of y equals 4. And note that we can slip this guy inside the natural log, so it becomes the natural log of the limit as x approaches 0 positive of y equals 4. Now, how do we get rid of a natural log? We apply the exponential function with a base of e. So we have an e here and e there. And so the left-hand side simply becomes the limit as x approaches 0 positive of y, and the right side becomes e to the 4th power. And there we are. That's our answer, because recall that y is the same as f of x, or this guy right here. All right, and that's everything from that section. Everything in L'Hopital's rule. We went over how to solve problems of an indeterminate forms. We started off with how do you deal with 0 divided by 0 and infinity divided by infinity. Then we moved on and we looked at indeterminate differences, that is infinity minus infinity. And basically the way we worked them is that we just factored out an x to some power. And then we looked at indeterminate forms. That is where we've got a power, right, where we have one function raised to another function, and the 3 different indeterminate forms that can pop up. And just to be clear, just because you have this scenario does not mean you're going to have an indeterminate form power. What gives you an indeterminate power is this guy, or this guy. Okay. So now we're going to go on to optimization problems. So basically this involves finding the best input for whatever mathematical model you're using. You could be trying to figure out the optimum amount of concrete to pour into a beam, because there's a certain point where it gets stronger and stronger, but you're also increasing the weight with the more concrete you're putting in. So there's a certain point where if you start putting in more concrete, you're actually hurting yourself. It's also, in the example I've written down here, is a truck driver, someone with a big cargo. They can get somewhere a lot faster if they drive faster. They may not have to deal with labor costs or such, but the faster you drive, the more fuel you expend, the more wear you put on your vehicle. So there's a certain speed that is the optimal speed. There's a certain speed that gives you the most profit. So in a business setting, oftentimes you use optimization problems when you're trying to figure out the amount you have to manufacture, the amount of the good that you're making. How many units do you have to make so that your cost is minimized or that your profit is maximized? And so these are only a very few examples of how this is used. Let's go ahead and look at two examples here. For this one, we're going to pretend, some of us may not have to pretend, but many of us do, that we are a farmer and we are fertilizing a certain crop. The yield, Y, is given by this equation right here, right, where K is a positive constant, and it's got to be experimentally determined, and N is the amount of nitrogen that you're putting into the soil. And we want to know, what is the optimum amount of nitrogen you want to add into the soil? So to do this, we have to figure out, okay, what is the optimal level? And so, that's going to be, we want to maximize our crop yield. So, the equation is going to look like this. All right, so we've got our function here. Note that I've put a restriction on here that the nitrogen level must be equal to or greater than 0. It doesn't make much sense for the nitrogen level to be less than 0. You can't have a negative nitrogen level. We set the constant equal to just 1. You can slide it around if you like, but all the constant's going to do is just affect the shape of the graph. Note the only requirement of the constant is that it is positive, and its actual true value will simply be experimentally determined anyways. And so we're looking for the maximum value, right? What gives us the maximum amount of crops. And so you can see, it's going to be right there. And you can even take a graph, like first derivative test will be sufficient. And we're going to work this through by hand, but I want you to see the graph of it so you can kind of really solidify what's going on. So let's call this, call it f of x. And this will be the derivative of, okay, I didn't like that, so I'll have to turn this into a function of n. Alright, so where that's 0, that's where that's going to be, right? So you can see they clearly match up. And so we expect that the crop level to be 1 right there. And so, but note that this positive constant here has no bearing on where that max is. All it does is affect how much of a max it is. So let's do this by hand now that we have a working picture, right? You can see that the derivative is positive, and then it's negative. First derivative test, if the derivative goes from positive to negative, then that means we've got a max right there. And so maximum crop yield, and of course how much we get depends on this constant here. So the better the constant, the better the yield. So let's go back, let's work this by hand. And so y prime, we're taking the derivative with respect to the nitrogen level. And so note we've got a function up top, function below. We're going to use the quotient rule to take the derivative here. And so derivative of the top, let's go ahead and use our old convention, because I did notice some of you guys were getting tripped up on these problems on the exam. Right, so first we take the derivative of that yellow part, which is k, and then simply multiply by the bottom. And then minus the top part, and then we multiply that by the derivative of the bottom, which is simply 2n. And so we have 1 plus n squared quantity squared, right? Don't forget to square the bottom. All right, so there it is. We've got our derivative. So this is a little bit difficult to look at, so why don't we go ahead and clean it up so we can see what's going on. So this becomes k plus kn squared minus 2kn squared. So don't forget the bottom here. There we go. All right, so note that we got two like terms here, and so that's going to further simplify. And so we're going to have k minus kn squared divided by 1 plus n squared quantity squared, and we can do one final simplification. We can factor out the k, and so we're left with 1 minus n squared over 1 plus n squared. All right, so let's take a look at where the critical numbers are. Anything that makes the bottom 0 will make it not exist. That counts as a critical number. Note there are no real numbers to make the bottom not exist. I'd have to actually go to an I, that is the square root of -1, to make it work. We're not concerned with imaginary numbers right now because we're dealing with actual fertilizer. But note up here we can find a critical number. We have two critical numbers. We've got n equals -1 and +1. And what are we dealing with? We're dealing with nitrogen that we're putting into the soil. You cannot put a -1 nitrogen level, so that means that this guy is out. And so 1 is our critical number. And so if you can apply the second derivative test, or you can simply just see what's going on before and after 1. You plug in 0 into this equation, and you will get a negative number. If you plug in anything more than 1, you will get if you plug in 0, you'll get a positive number. And if you plug in anything greater than 1, you will get a negative number. So, for instance, y prime at 0 equals k times 1 minus 0 squared over 1 plus 0. What are you going to get? Well, you're going to get k, right? A positive k, and k is positive always. And then just plug in anything after 1, right? Because there's no more critical numbers. It's not going to change. We can just plug in a 2. And so k over 1 minus 4 over 1 plus 4 quantity squared. Well, of course, that's going to be a negative number. So negative number times k. All right, and so that would be, in case you're working that out, -3 over 25. All right, so that's an application of the first derivative test, right? Because there's 1, the derivative is positive before, negative after, and equals 0 right there, right? We got our min. And so the optimal nitrogen level is n equals 1. And your crop yields that you can expect, just plug 1 in. That's going to be k times 1 over 1 plus 1 squared, so it would be k divided by 2. Right? That would be your optimum crop yield. Okay, example 2. we are enclosing 3 sides of a rectangular plot with a fence. We can afford 24,000 linear feet of fence, and we're going to use every last dime in our budget on this fence. I don't know why, but we are. What dimensions of the rectangle will allow us to enclose the most area? All right, so we're assuming that, we're trying to enclose an area, and let's just say maybe it's butting up against a river. We're trying to get our cattle to have the most grazing area, whatever scenario you wish to employ. Okay. So here's our 3-sided fence. It's open to the water. And so this side we're going to call X. This side we'll go ahead and call Y. And so our perimeter equation is going to be 2 times X plus Y. And we know what our perimeter is going to be. Our perimeter is going to be 24,000 linear feet. And then we got to ask ourselves, okay, what other equations do we know that's going to help us? Well, we're interested in area. Area is what we're trying to maximize. So what is our area equation? Well, that's simply X times Y. And so we want to take the derivative of the area to find the optimal level. And let's see, we're going to go ahead and do dA dx. So first thing we got to do is we got to get y in terms of x. And so we're just going to come over here. We're going to rewrite this guy. And so this is going to become y equals 24,000 minus 2x. And so we can plug this in. We can go ahead and factor out a 2. That might help us. So we have 12,000 minus x. And so then this whole thing becomes 2x times 12,000 minus x. Okay. So now we take the derivative. Alright, so note this is product rule. So derivative of 2x is just 2, so we have 12,000. Okay, and then plus 2x, and then the derivative of what's in there, which is just negative 1. Alright, so what does this all become? This becomes, so we've got 12,000 minus x, so it becomes minus 2x. Alright, just combining this x with this x right there, both negative. Alright, so the next thing we got to do is we got to figure out, okay, when is the derivative 0, right? We want to know what is the critical number, because that's the only time that our function can change from going up to going back down, right? That's the point, that's the first derivative test. That's the point of maximum area. So we're going to set the derivative of the area equal to 0. And so since we're saying equal to 0, I'm going to go and divide both sides by 2 right off the bat. So we get 12,000 minus 2x, solve for x, and we get 6,000 feet. All right, so now we know that I'm already using blue. Let's go ahead and use a different color. We'll go with this guy. So 6,000 feet. So everywhere you see this highlight, that is 6,000. All right, so that's awesome. We still want to know what this dimension is. But all we got to do is plug in 6,000 into our perimeter equation that we have up here. Already solved for y. Alright, so we're plugging in the y, the x to find the y, and so we have y equals 24,000 minus 2 times 6,000. which will get us 12,000 square feet, linear feet. And there's our other result. So 12,000 square feet. Let's go ahead and use the appropriate highlighter. There we go. All right. If you have any questions, feel free to email me. Otherwise, have a good day.